Algebra 2, state sample question number 20 and probably 21 and maybe even 22. We'll see. So if the terminal side of angle theta in standard position passes through point 4 negative 4, 3, what is the numerical value of sine theta? As a general rule, anytime it's a trig question that talks about points or triangles or something like that, and they do not give you a picture, you should draw yourself a sketch. So angle theta passes through the point negative 4, 3. So negative 4, 3, left 4, up 3. Here is the point negative 4, 3. And they're telling us that angle theta is in standard position, so that means it's passing through this point. That's angle theta is represented here. But we know that whenever we did trig on the xy axes, we like to work with triangles. I mean, trig is the prefix tri, is the prefix for 3, triangle, trinomial, trig, tricycle, all that stuff. So we like to work with triangles, specifically right triangles when we're doing trig. And obviously we know it's trig because we're talking about sine theta. So this is angle theta, but you know, a triangle over here is not really going to work out. So what we do is we can use reference angles, and I can make the triangle here. The terminal side of the angle is where it ends. The initial side is where it begins. But basically, wherever your angle is, if you have an angle in the first quadrant, you draw a triangle to the x-axis. If you have an angle in the second quadrant, you still draw the triangle to the x-axis. If you have a triangle in the third quadrant, you still draw the triangle to the x-axis. And if you have an angle in the fourth quadrant, you still draw the triangle to the x-axis. We always draw our right triangles to the x-axis. They're always connected to the origin, out, and then to the x-axis. So here's your quadrant 1, your quadrant 2, quadrant 3, free sloppy, and quadrant 4. Triangles, it kind of looks like a bow tie when you draw them all together. So anyways, the fact that this is negative positive, a negative x, a positive y, tells me that it's a quadrant 2 triangle. Now that's helpful for a couple of things. I want sine theta, and if you remember your ASTC, that reminds us that in quadrant 2, sine is positive, so these negative values aren't going to make a whole lot of sense. Tangent and cosine are negative, but sine is positive in that quadrant. Now, where does this come from again? A little quick refresher on that. Remembering that the opposite of the value of the theta is essentially the y value, right? Opposite over hypotenuse, with the hypotenuse being 1 when we work on unit circles. Not the case here, but the opposite is the y value, and the adjacent is the x value. So when we think about x and y, we can relate it to cosine and sine. And so in the first quadrant, with x and y both positive, that means that sine and cosine and tangent are positive, because they're all positive if you're working with just positive numbers. But in quadrant 2, we have a negative x value paired with a positive y value. The negative x tells us that cosine is negative. The positive y tells us sine is positive. And since tangent is really sine divided by cosine, anytime you divide a positive and negative together, the division, the quotient is negative. So tangent would be negative there. In quadrant 3, you have a negative x and a negative y. So cosine and sine are both negative, but when you divide a negative by a negative, you get positive. That's why tangent's positive there. And in quadrant 4, you have a positive x, negative y. The positive x is y cosine's positive. The negative y is sine negative. One of each divides to negative. So in these 3 quadrants, only one of the 3 basic functions is positive, the other 2 negative. In quadrant 1, they're all positive. Now, as far as their reciprocals go, you know, cosecant would be positive here, cotangent here, and secant here. You know, they are just the reciprocals of these, so their signs match up there. But anyways, back to this problem. So we draw a triangle in the second quadrant that corresponds to about where this angle is said to go through that point. Now, that point negative 4, 3 is not just to tell us that it's in the second quadrant. It's to tell us that this is negative 4 and this is 3. We went over 4, up 3. The x value is the adjacent, the y value is opposite, and that's just how coordinates work. But Pythagorean theorem can be used on these to get that this side must be 5. 3, 4, 5 is a common one, but you could do 3 squared plus negative 4 squared equals c squared, or whatever letter you want to put there. But now that we have that, we can say that sine theta, opposite over hypotenuse, theta is always at the origin, is 3 over 5. So draw yourself a little sketch, and it's really not a bad problem. Of course, you need to remember sines, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent, and remember that x corresponds to cosine, y corresponds to sine, and your ASTC, and how to draw the triangles. So, this is a simple question, but there's a lot of information behind it that makes it simple. 21. Study of the annual population of the red-winged blackbird in Fort Mill and South Carolina shows the population B of t can be represented by the function B of t equals 750 times 1.16 to the t, where t represents the number of years since the study began. In terms of the monthly growth rate, the population of the birds can be approximated by what? Now, when I first looked at this question, monthly growth rate, I kind of thought they were saying, all right, well, if you do compounded monthly, that is not the case here. A monthly growth rate is not the same thing as compounding monthly. So, because, these are exponential functions. An exponential function with an annual rate versus a compounded rate are going to be two different things. Like if you have a savings account where your interest is applied annually once a year versus compounded monthly, that's 12 times a year, you're going to get different numbers in the end. And what they're trying to say here is this is the formula for the population of these birds. But this formula is represented in an annual format. We want to represent it in a monthly format, but it's still the same equation. So I'm trying to not get a different equation and compounding it annually versus quarterly versus monthly, stuff like that. That'll give you different equations, different answers in the end. They're different functions. But I'm trying to rewrite this in a different way, but the same equation, kind of like how 1 over 2 is the same as 5 over 10 is the same as 10 over 20, right? It's almost like I want to rewrite it in an equivalent form, but expressed in a monthly form. And basically what I want is I want the 12 in the exponents. That's how you can kind of tell it's expressed monthly, is if the 12's in the exponent. If I wanted it expressed quarterly, I'd have 4t as the exponent, or biannually, I'd have 2t in the exponent. So I want 12 in the exponent, not over 12, but 12t. But not only that, if I just make it 12t, this can't stay the same. Like, these are going to be two completely different functions. If everything else is the same except one's t, one's 12t, one's being raised to the 12, one's not, that they're going to be very different answers. Again, I'm looking for an equivalent function. So that's the wrong answer, and here's the answer, but let me explain why. Where did this come from? Basically, so 750 parentheses 1.16 parentheses to the t. If I want this to be 12t, I can't just raise something to the 12th and not change it. What I would need to do is raise it to the 12th, to 12 and the 12th. And the reason for that is because when you raise an exponent by an exponent, they multiply. And a 12th times 12 is 1. So if I take a number like, if I take the number 5 and raise it to the 1/3, that didn't work out. Hold on, let me get rid of it. So 5 raised to the 3rd. But then I take that answer and I cube it. I'm back to just being 5. So if you take something and raise it to the 12th and 12, it's really not doing anything. And that's the point, is I'm not trying to change the actual value of this equation. I just want it written a little bit differently in a monthly format. So I can change the exponent from t to 12t if I also change it to the 12th. And this 1.16 to the 12th, that's where the 1.012 comes from. So you have to change your base, raising it to the 12th, and then that allows you, I don't know, I keep raising the exponent by the exponent, and that allows you to then, have your, and it's rounded, of course, and that allows you then to also have 12t there. So it's kind of a weird thing that we're doing here, is we're writing the same equation in kind of a different way. But it's a simple procedure. If I want 12 in the exponent, I also have to raise it by the 12th and 12. This way, I'm not actually changing anything, just the appearance of how it's written. All right, how are we doing on time? We're at about the 10-minute mark, but I want to just get one more in here, do all three together. So use the properties of rational exponents to determine the value of y for the equation. So here are your exponents rules, and basically a couple of things. Um, a to the, b over c can be written as the c root of a to the b, right? Fraction exponents. The bottom is a, the root power. The top, the numerator exponent's like a regular exponent. So this cubed root of x to the eighth, that can be written as x to the 8/3, where the 3 is the root and stuff like that. So I'm going to write them as fraction exponents because that's a little bit easier. On the bottom here, we have that same rule that an exponent raised by an exponent is multiplied, like what I was talking about, how a 12th raised to 12 is really just 1, because the 12 times 12 is 1. Well, this can be written as x to the 4 times a third is 4/3. And then simply when we divide a common base, we subtract our exponents. So I have to subtract 8/3 minus 4/3. And 8/3 minus 4/3 is 4/3. And it's kind of weird how they write this, but they say that this equals x to the y. So this equals x to the y, and they want you to solve for y. So they want you to solve for the exponent of this whole thing, which we just did. So y equals 4/3. So kind of a weird way of asking this question, but it has a couple of exponent properties tied to it. The connection between fraction exponents and how to write it in radical form. Exponent raised by an exponent is multiplied. Dividing a common base, you subtract the exponents. What didn't come up here in the common exponent theme is, a negative exponent causes a reciprocal, relationship. Again, didn't come up here, but that could be something that comes up a lot with this. And so that's really it. So that's a short one. So all right, we covered 20, a little bit of trig review there, some important concepts in there. 21, kind of a strange exponential thing, how to write it differently, just raised by an exponent and its exponent's reciprocal. That's what 12 and a 12th are, the reciprocals. So raising by a reciprocal and it's, doesn't really do anything, it just kind of allows us to write it a little bit differently. And then some important exponent properties here. All right, so there's all 3 sample questions for you. See ya.